last episode, we just finished our DC bench power supply circuit. And let's say we have around 20 volt, plus 20 volt and minus 20 volt. So what we actually need right now is a typical lab power supply monitoring circuit. Or we could say we need a multimeter to measure voltage and current for the output rails. So this is the concept to actually build the monitoring circuit. So we have 4 steps. We already finished the step 1 in the last episode. We already have the power supply circuit. Then we moved to step 2. Now we are using resistors and op-amp. So resistor is used to scale down the value, and the op-amp is used to amplify that signal. And then in step 3, we put that signal into the analog pins of the Arduino Nano, and then we write some code and convert that signal into the real display, the real value, and we display the value to the monitor. For a positive rail, if we want to measure the voltage, we must use resistors to scale out the value in a range between 0 and 5. So this is the range for the Arduino Nano analog pins to read. And for the current measuring, we use a sun resistor and an op-amp. That is why we already have 2 sun resistor, the 2 white sun resistor in the last episode. And for the negative measurement, for the voltage, we must have a virtual round, because since the Arduino Nano cannot read the negative voltage, so we must flip the negative voltage into the positive region. And then we use an op-amp. So we use an op-amp to actually create a virtual round and then amplify that signal to the analog pins. And for the current, we use the same idea of the positive one. We still use the sun resistor and an op-amp. And one thing I must remind you is the analog pins can only read between 0 and 5 volt. And it scales the value into 1024 value, 1024 digit. So we must scale down every value to 0 and 5. That is why 20 volt is too large to read, so we must get out 20 volt to 5 volt, let's say, and then 0 volt to, let's say, 0 volt. So this is the concept, okay? So 5 volt is nearly 20 volt, 0 volt is 0 volt. Let's start with the easiest first. This is the positive voltage measurement. In this circuit, we don't need an op-amp. Like I just said before, we actually don't need an op-amp to measuring positive voltage. We only need 2 resistors and 1 capacitor. So this is the very familiar voltage divider formula. So based on this setup, we can calculate the voltage in this node right here, and then we will use this voltage and put this voltage into the analog pin. So let's say VDD is 0 volt, and then the voltage in this node we will get is 0 multiplied by 68,000 divided by 68,000 plus 330,000. So we have 0. Oh, wait a minute, I don't need to actually put it in the calculation. So this is 8. Let's say if the VDD is 8 from the power supply, and voltage at this node will be 1.36 volt. And if the voltage is 20, the maximum voltage at this node will be 3.41 volt. So what can we learn from this? From 0 to 20, the scale only around 0 to 3.4 volt. So this is the maximum, which is equal 20 volt. And with the lowest 0, we have 0 at this node right here. So we already scaled the value of 0 to 20 into 0 to 5 range. Okay, actually this is 0 to around 4 range. So therefore no op-amp is needed, and we can use it for Arduino. Since the analog pins is functioning around 0 to 5 volts, this is the safe limit. And why we have the capacitor right here? Because we use this capacitor to filter the ripple voltage and noise. So let's say without this capacitor, the DC signal will be fluctuating like this, and with capacitor the signal will be smoothed out, so the graph will probably look like this, and then the Arduino can read the value better. And one thing I want to give a note about is why we use 330k and 60k instead of not just using 330 and 68 ohm resistors. The problem is we're using the large value because we want to minimize the current across these resistors. So we want to minimize the currents as small as possible. So we want the I is small because we don't want to waste the energy. Okay, so with these huge value of resistors, we're just saving a lot of energy. So we can so actually the current flow through this circuit right here with the maximum voltage is 20, the current is only 50 microamps, so basically pretty small. And 50 microamps is in the range of 20 and 40 milliamps maximum. So after we finishing the setup with the circuit right here for the positive voltage measurement, and now we need a code to put it in the Arduino, and we just need to reconvert these value right here into these value right here. You know what I'm saying? So if your analog pins is reading 3.4 volt, then you put it in your code, in your firmware, that this value is 20. So it's actually 20 volt we are measuring. Okay, so it's just we just like reverse engineer. So to measuring the current, the positive current, we will use a technique called current sensing, and this technique require Ohm's law. Okay, so I will give you an idea to understand. So if we want to measure the current flow between this node right here and this node, then this node right here to ground, so we need to measuring the voltage drop between this node right here. So we need to use a very small value of sun resistor. So this require a small sun resistor with the enough power rating to handle the current flow through it. So that's why I choose the sun resistor with the power rating is 5 watts, and the value of the resistor is 0.01 ohm, because this value is very small, so the voltage drop between this node right here is pretty precise for me. So this is the idea. You read the voltage at this node, okay, so then you convert it into the current in mathematical way. And I also have this load right here. We're using this symbol right here with 10 ohms to represent the load. So let's say if your VDD is 20, if your VDD is 20 and your load is 10 ohm, and therefore you can calculate the current flow between VDD to ground is 2 amps. So you have, no, actually plus 0.01 because we have another resistor right here. So this is the current flow, nearly 2 amps. So actually in real life, the current cannot be more than 1.5 amp because the IC I use can only supply around 1.5 amp, and it cannot exceed the value. So in calculator this is correct, 2 amps, but in real life only 1.5 is maximum. So okay, and next we need to take a look is we don't actually put a lot of current into the op-amp. Okay, there's only a very small amount of current goes into the op-amp, so we just neglect it. Okay, let's talk about the sun voltage. We are using Ohm's law, and this is the very basic formula. V sun equal to the current plus the sun resistor. So let's say the current is 1.5 amps, and then you can calculate the sun resistor. The sun voltage is around 1.5 multiplied by 0.01, then you have 15 millivolt. So the number just said that if the current flow through this circuit is 1.5 amp, what you get is 15 millivolt right here. So this is the 15 millivolt you can get, and actually it is very precise, but it is too small for the Arduino analog pins to read. So what we need is an op-amp right here to amplify the signal, and we need to amplify that millivolt range into the 0 to 5 volt range. Okay, and then we have this op-amp, and this configuration, as you can see right here, is the non-inverting amplifier. So we need to amplify the sun, the voltage of the sun resistor right here. We need to amplify it into the range of 0 to 5 volts that the Arduino pins, the analog pins, can read. And we don't need to invert it, we just need to amplify it. So we must put it in the configuration that using that without okay, just put it in non-inverting amplifier. Okay, and this is the schematic. So you have a resistor right here, 230,000 ohms, and this is 1,000 ohm. You actually don't need to follow the exact resistor. You can just need to follow the ratio that I put in here. The gain ratio is around 231, so you can choose whatever resistor value that fit the ratio. And I will give you the example. Let's say the current flows through this circuit is 0.5 amps. Okay, therefore the sun resistor, the sun voltage will be around 50 millivolt. Okay, so 50 millivolt is too small for the Arduino to read, so we actually need to amplify it through this op-amp right here, and this is the op-amp output. So we need to amplify it, and then after it is amplified, 50 millivolt is right now is, oh, my mistake, actually 0.5 multiplied by 0.01 is equal to 5 millivolt. So my mistake, sorry. So 5 millivolt is too small for the Arduino to read, so we must amplify this voltage into the scale between 0 to 5 volt. Okay, so let's say 5 multiplied by 231. So because this is the gain, okay, this is the gain is 231. So 5 multiplied by 231, I mean 0.005 is 1.1 volts, around that. So this is the voltage at this node right here. So this is analog pins A1. Okay, so this is analog pin A1, and this pin read around 1.15 volt. So this is between the scale of 0 to 5. So it is perfectly fit in the scale. And let's say if the current is 1 amp, 1 multiplied by the resistor value, we have 10 millivolt. So this is 10 millivolt, and 10 millivolt, and 10 millivolt multiplied by 231, we get is 2.3 volt. And if the current is 1.5 amp, the sun value will be around 15 millivolt. And 15 multiplied by 231, what we get is 3.465 volt. Okay, so this is the peak voltage. So you just need to write a code that convert these voltage value between into the real current. So you just need to write a code that said if the analog pins sends 3.46 volt, so the current is actually 1.5 amp. And we also doing the same with the 1.15 volt, the current is 0.5 amps. Okay, so pretty easy, right? So it's just a technique. I would say again, first you put a shunt resistor between the circuit right here, the current flows, and then you measure a little bit voltage drop right here at this node, and then you amplify that voltage into the range that Arduino can read, which is 0 to 5 volt. Okay, pretty easy. And you can see I put a resistor 1K right here and 1 microfarad right here. So this configuration, I create a low pass filter because actually this is not a perfect DC signal, okay? It has noise, so we need to filter out the noise. So we just combine this capacitor and this resistor, we create the low pass filter. And this is the formula of the low pass filter. The signal below 159 can pass, but the signals above 159 is getting filtered. Okay, so this is the concept. And if you put a resistor right here, which is 1K, it actually protect the circuit. So let's say somehow the op-amp output more than 5 volt. Okay, somehow, although we already supply 0 to 5 volt, probably the output can be cut off if the output voltage is more than 5 volts. But let's say I'm power the op-amp with 10 volts right here, and then somehow the op-amp output voltage is 7 volts right here. So the op-amp voltage is 7, and Arduino pin voltage clamps at 5 volts. So 7 minus 5 divided by the resistor value right here. What we get is 2 milliamps across this resistor, right? So if somehow the op-amp output 7 volt and this analog pins clamps at 5 volt, so the current flowing into the analog pins is only around 2 milliamps, which is very small, okay? Too small. So it cannot damage the analog pin. So without this resistor, maybe something would fail if the circuit goes wrong, okay? It's just the protection. And yep, this is basically the concept of current measurement. Again, remember to choose wisely, because you cannot measuring the current with the small sun resistor, because the current will actually burn out the resistor. You need to choose the resistor that has the power rating enough to handle the current. So let's say this sun resistor right here is 5 watts. So this is the maximum power rating, and the value is 0.01. So the current pass is, let's say the current is 1.5 amps multiplied by 0.01. So this is the power through the resistor, okay? So this is the power consumption. So this resistor is 5 watts, and this is not even close to 1 watt, but actually you still need 5 watts or like a little bit less to ensure the heat dissipation, okay? So don't use a small resistor, the carbon film, you know, the small one. Just don't use it. To measure the negative voltage, actually we can do the first trick, the positive measurement trick. So we only need the voltage divider trick to actually measure the negative voltage. So it's actually the same. It's not anything fancy, but I want to do it in the hardcore mode because it is too easy for me. All right, so using the same trick, the voltage divider one, is too easy to do it. I want to level up my knowledge, so I'm trying to do it in the crazy way. So instead of using the divider trick, now we need to use 2 op-amp. So this method can give you precise measurement instead of the divider trick that I just used for the positive one. So op-amp is powered 0 volt and 5 volt. It is not dual supply, so we only feed the positive voltage into the op-amp, so the op-amp cannot sense negative voltage. Then the op-amp, so we must have a virtual ground to actually flip the voltage into the positive region. So we flip the negative voltage into the positive region, and so we can amplify that signal and we put it into the analog pins. All right, it is very complicated. I think so, pretty sophisticated. So if you don't want to use this method right here, you can just stick with the basic voltage divider, but I want to challenge myself, so I learned it. Okay, so first we have one op-amp to act as the stable virtual ground. So we have the VCC right here. So this is the 5-volt supply. You can get it from the Arduino 5-volt pin or whatever 5-volt supply you have. And then you put it in this voltage divider like this. So based on the calculation, I already did it. The voltage at this node right here is 1 volt. So this is 1 volt. Actually, if you want a virtual ground and the virtual ground is 1 volt, you can stop right at this step. You don't need an op-amp anymore. But if you want a very stable source, like a stable 1 volt virtual ground, you need an op-amp to be a buffer. Okay, so put it into the op-amp. So this op-amp is non-inverting configuration, and the gain is 1 because 1 plus 0 divided by 0 is 1. No resistor, so 0 and 0. So the gain is 1. We put it 1 volt in and then 1 volt out. Pretty easy, right? So this is the virtual ground, or we can say it is the V reference. Then we put the V reference into the positive node, the positive input of another op-amp right here, as you can see. And you put the op-amp with the resistor with the configuration as the inverting mode right here. So you can choose whatever value you want. I choose 150 and 10k. That is based on me. You can choose whatever you want. It must satisfy the ratio. So this is the formula under here. We have the standard equation. If the V reference is equal to 0 or V reference is ground. So this is the standard equation, but we don't use this. We use the equation that V reference higher than 0 volt. Let's say 1 volt because the V reference is 1 volt right here. So this is the equation for the inverting amplifier. And so we put it in the so we put all of these in the calculation. We can calculate the output right here, the output of the analog pins A3. So this is the VSS, which is the negative rail, the negative voltage. So we supply the negative voltage from this node right here. This is 150k ohm. This resistor is the Rin of the inverting amplifier right here. So this is Rin, and this 10k is RF. So this 10k is RF, and V reference is 1, and Vin is this VSS right here, and Vin is equal to -20. So let's put everything into the calculation. We have 1 minus RF is 10,000 divided by 150,000 multiplied by the Vn is -20 minus Vref is 1. So right here it's just output 2.4 volt if the negative voltage is -20. All right, so pretty easy, right? As I just said before. So I will put the comparison table like this. So A3 is 2.4 volt if the input is -20 volt. So if the input is 1.25, let's say, the output is 1.15 volt, and if the output, let's say 10 volts minus 10 volt, the A3 would be 1.73 volt. So you just need to write a code that convert these value right here into these value right here. Okay, pretty easy, right? And you actually don't need to follow the same resistor that I chose like this. You can do whatever you want. Okay, you just need to satisfy the output ratio right here, the output right here. So just need to put it in the range between 0 and 5 volt, the output right here, the output, and you would be fine. Okay, I put the capacitor just to filter out the noise, and this is just for protection. And these combine, we have the same concept with the low pass filter right here. Okay, so very familiar. And for the last one is the negative current measurement. So this is, we are using the same concept. So this is A4. So we are using the same concept with the positive current measurement, but we must carefully check the sun resistor position right here. So let's say we are as you can see, we are using the same concept with the positive current measurement, but there's only a little difference right here. So because in negative rail, the current is actually flowing from ground to the VSS, and VSS is let's say minus 20 volt, because current flows from the high potential to lower potential. So this is the actual current flow. Therefore, we must put a sun resistor right here between the VSS and the R load right here, and on the top is ground. So this is the actual current flow. Current doesn't flow from VSS to ground. Okay, so because it doesn't make any sense. So this is very basic knowledge of electronic and electrical stuff. All right, so pretty easy. Same concept with the positive current measurement. Since I have the fuse connected to my circuit, I will showing you guys how I can calculate the fuse type for the transformer. So first, I connected the fuse directly to the transformer primary coil. So what we need is a time delay slow blow fuse with the voltage rating higher than 250 volt AC. This is for safety, and the current rating is around 120 to 150% of the transformer primary current. So the problem is why we are using the slow blow fuse. Transformer causes a high inrush current, often 5 to 10 times the steady state current. It costs around for a few milliseconds when first powered on. So if we are using a fast blow fuse, it just might blow right up. So we need a slow blow fuses, allow short inrush surge, but still protect against the overcurrent. So first, we are using the transformer, and transformer causes a high inrush current, and inrush current can only be used, can only protected by the slow blow fuse, and we must to have the voltage rating higher than 250 volt AC for the safety, because we're using the power AC from the outlets of our home. Now I will show you how to calculate the fuse current rating. So the formula is I equal P divided by V. So this is the very general formula. If you want, you can add a little bit efficiency right here, and you put it around 90% because this is the efficiency for the transformer in real world, and then you put it in the calculation. So my transformer has the power rating is 30 VA, so we can say it's around 30 watts, and the voltage of the primary coil is 230 volts because we're using the AC again, and this is the efficiency, which is 90%, 0.9. And just remember, this is the output power of the transformer. So this is the secondary coil output, this is the primary coil input voltage, and then we put it in the calculator. We have 0.145 amps. So we need to multiply this value right here to around 120 and 150% margin. So let's say I multiply that value with 1.5, and then we have 0.2020 amps. So this is the safety current rating for the fuse. Okay, so let's say you can choose a fuse for in the electronic shop, whatever shop you have. You can choose 250 volt for the voltage rating and around 250 milliamps slow blow fuse. Okay, so just keep in mind that you must have the voltage rating in a safe value. Don't you must not lower than 230 volt AC. Okay, because it just might blow right up, and the current for the fuse would be around this safe level. Okay, and you must use a slow blow fuse.
All right, so I will. We just already finished the circuit design phase, so I'm gonna move to the simulation process. Okay, so this is the circuit we just designed. So I put it on the Nemotism software. So this software I use to simulate the circuit, the behavior of the voltage. So in the last episode, we already finished the DC power supply circuit like this, and now we want to measure the voltage at these three terminals, right? So this is the positive terminal, this is the ground, and this is the negative terminal. Oh, by the way, you also need to include the fuse right here. So I just designed the fuse for you too. So you need to include the fuse right here. And now we move to the voltage and current design. So let's say VDD. VDD is the positive rail from the DC power supply right here, and VSS is the negative terminal of the power supply, and VCC is just a constant 5 volt, so it's not from the DC power supply, so we just neglect that. Okay, so to start with, let's start with the easiest first. This is the positive voltage measurement. So like we just designed, when the voltage is 20, when the voltage is 20, the output would be the 3.4 volt. So we put this into the analog pin A0, so it reads the voltage. So if the voltage is, let's say, 1.25, the minimum from the DC power supply, so the voltage into the analog pins A0 is just above 0 volt a little bit. So you just need to convert this value. By the way, you can check the calculation I gave you before to compare with the value you have on the simulation. So this is the positive measurement. Next we have the first op-amp. Oh, by the way, I use 4 op-amp, but instead of using 4 separate op-amp, I mean like 4 ICs, you can just choose an IC, the integrated circuit. That is include 4 op-amps. So I choose LM324. So this chip included 4 op-amps already inside, so you don't need 4 separate chip. Uh, so this is the part for the virtual ground. So based on this setup, this is the input 5-volt constant. So we put the 5-volt for the supply to the op-amp, and then what we have is constant 1 volt. As you can see right here, 1 volt, close to 1 volt. So this is the virtual ground 1 volt, and this part is the current sensing for the positive one. As you can see, if the voltage, let's say the voltage is 20 and the load is 10, what you get is 3.5 at most. So you just put it in the calculation inside the Arduino. This is the negative voltage measurement. So based on this setup, again, if the voltage is minus 1.25, the multimeter said it is 1.1 output. So you connect this output into the analog pin A2. So A2 is used for measure negative voltage. And also the same with the current sensing for the negative one. So this is the negative current sensing. Please note that this setup is a little bit different from what I did on the paper on my notebook, because the simulation is not working with the correct setup. So I must do a little trick. So this is should be ground, okay? This shouldn't be VDD 20 volt. This shouldn't be like that. This should be ground. And this part right here is not ground, okay? This should be VDD. I mean VSS right here. So VSS should be this part, and VDD should be the ground. All right. So this is the real world behavior, and but on the simulation, it's just not working, and I just figured out how to put a simulation everything's together. So as you can see, if the voltage is minus 20, so this is minus 20, okay, 3.5. And if the voltage is lower, the outputs change. And so you connect this output to the analog pin A4. Same concept, pretty easy, right? And then you put everything inside the Arduino code like this. It's only around 200 lines of code, and I will showing you step by step. Please note that the code is not working perfectly for my circuit because I soldered by hand, and I was messing up all the time, so I need to do a little adjustment for the mathematical part. Okay, as you can see right here, first we're including the libraries to write a code because we are trying to put the to display the value on the Oled screen, the monitor. So we need to have the library for the added proof. So this is the driver I'm using. This is the driver for my screen, and this is the pixel of my screen. I just defined it, reset it, was inside the library, and this part is my logo. Okay, this is my logo. So if you want to have your logo like this, you go to the online web. So I will leave a link down below in the description. So choose the file like this. Wait, all right. So choose the file, you generate a code. So this is the code. You just need to copy the code, then it's good to go. So you put all the code right here. The problem is you must convert it into bitmap, okay? The bitmap style. Okay, so this is the setup function, the void. So you must have these initial code right here to display, I mean to start the screen. First you need to begin it, initialize the Oled. Now we do the clear, because we must make sure the OLED is good. We clear every leftover pixel. Okay, so we set the pixel. So we set the text size. I set it to 1. 1 is enough for me. And we set the color is white. For my screen, the only color is white. So if you choose this to be like blue, this just doesn't working, and you might see an error. So I call out the logo, my logo right here. So this is the function below for my logo. So you can actually, I don't want to explain too much about the function. You can put it on the ChatGPT. I think it's better for you to understand. So I will explain the math inside the code. First you first you create a loop right here. Oh, by the way, there's the pull up resistor external. So I already solder the external pull up resistor because I want to have a switch to stop the screen from like jumping value stuff. So I want to freeze the value, freeze the number, because the number just changing all the time. It's not constant. So I want to freeze the value in the range I want. So I need the pull-up resistor. You actually don't need external pull-up resistor because inside the Arduino there is an internal pull-up resistor. So you just need to call out it. For me, I just want a physical one. I don't need to call out the internal one. So I just solder the external one. So this is the loop. So this first line right here, this is for the pull-up resistor. The pull-up resistor is always in high value 5 volt. Therefore, the code is constantly working. So it means that the screen is constantly working. It's constantly displaying the value. And when we press the button, bin D2, bin D2 is low, so everything is freeze on the screen. So the value is not changing. But inside, it is still changing a lot. But it just doesn't display it on the screen, okay? So it just frees the value for us to easy to look. So we just clear the display, set the text, the cursor, display the text stuff. Okay, move to this line right here. So you have to define 4 analog pins. All right. And the analog pins has the value from 0 to 100,023. First, for the positive voltage, this is the math, very basic. Just need to put it inside. You because there's many way to do the math. You just need to follow these basic instruction right here. The actual math is this line right here. So this is the actual one. But this is actually correct. This is actually correct, but not for my circuit. So if you download this code and you follow the same schematic of me, you should delete this line right here, and you should remove the comment like this. Okay, so because actually this is the correct math, but since my code is not working correctly, I chose this line right here because it's just a change in linear, and I put it on the chat GPT and it just solved for me because something is not working inside the circuit. Okay, but theory is correct. Theoretically, theoretically it is correct. Now we display the value that we just convert on the screen with two decimal places down to the negative voltage. We also scale down the value to the range of 1023. We scale down 0 to 5 to 0 to 1023. And then again, it should be this line right here because the mathematic is based on the math is based on the resistor. So actually, you can put it on a chat GPT to create a math for you, and you need to follow. But for me, it's just again something is not working perfectly, so I just put it on the I mean, I don't know what it is, the dash. I just put it on the dash, and then you go. And this is the negative math that I chose. Again, uh, only works only work for my circuit. Please double check. Don't worry, I will leave the code on the description. All right. So for the positive current, so this is the positive current. Actually, the positive current, I think it is working pretty good. So I don't need to do the different math. I just need to convert it to the scale of 0 to 1023, and then I divide it by the value of by the value of the resistor stuff. So it's pretty easy. You can put it on the ChatGPT to follow the mathematical conversion, and then we display it pretty good to the negative. So actually, in my circuit, the negative current is not working. So as you can see, there's nothing changed when I connect the negative. There's nothing changed when I connect the negative terminal to power an LED, for example. So it doesn't change anything. So it cannot measure it because I think there's an op-amp inside. Is just blow right up. Um, so this part is just for fun, I guess. I just put it like this. I put a zero inside for not displaying any value. But if your circuit is working perfectly, you should follow this line right here. So this is the math. I already I already put it in. All right, now it's done. So this is the serial number. This is for the checking session only. So you turn it on and you turn on the serial monitor under here. But I already finished the checking, so don't need to do it. Now we display it. Okay, pretty easy, right? If you don't understand any lines of code inside here, you can just put it on the ChatGPT entire code